In Cycle 1, Lesson 13, we're going to look at transformation of trig functions. We've already talked about transformations of other functions. Luckily, we're going to be using the exact same formula, the same letters, A, K, D, and C. It's just what are the parent functions. So we have A, K, D, and C. I usually just highlight to make things pop out of the page a little bit more. So I'll highlight the A values in yellow and the K in green and the D in blue and the C in pink, so that when we see them, I can color code them. But what you'll notice is what's left, the parent function, is just y equals sine x, y equals cos x, y equals tan x. So we know those parent functions, we know the features of them from previous lessons. Now it's time to apply the transformations. We know also the transformation formula, the mapping formula that goes xy maps onto x over k plus d, ay plus c. However, I'm going to suggest that maybe we don't need to actually use that for at least, we can use that for sure, but we maybe don't need to use that for some of these simpler transformations. We can always go back and use it. Maybe I'll do one example at least where we do use the mapping, but no need to use it to overkill and use it always. So hopefully you'll see what I mean as I go along. So first one, we're just going to do a vertical translation. We're going to add a C value. So we know that that is our vertical shift, right? A is our vertical stretch, K is our horizontal stretch, D is our horizontal shift, and C is our vertical shift. So y equals sine x, that's our parent function. Let's just graph that in blue. So I know there's 5 points that I know off, like the back of my hand, off the top of my head for y equals sine x. And here they are. I'll put them on the graph right now. So I can always go to those 5 points and quickly draw a sine curve. And of course it goes on forever at both ends, with arrows at both ends, but I probably won't bother with the arrows after this one, but it'll be understood that they do go on forever. So that's this one. The next one has got a C value of +2. Otherwise, it's exactly the same. And I just realized that there's no scale on here. I was assuming that the scale here was 1 and -1, but there's not going to be enough room if I do that. So I'm going to have to redo. Let's do a quick redo. That's the good news about it being quick. Let's do a quick redo, and I'll go 1, 2, 3, 4 like that. That means I do have to change my points slightly to make it fit better. There, all fixed. All right, so benefits of being able to sketch the sine curve quickly. So, +2, C value moves everything up by 2. So this point moves up by 2, this one up by 2, and so on. All the points move up by 2. And the graph has exactly the same shape when you're doing a shift. It's just up higher in this case. This one's got a C value of -3. So I'm going to take my blue graph and shift all the points down by 3. Not the most pretty. Yeah, I can't take that. I got to fix it. Let's see if I can do better this time. That's a bit better. Okay, there is that one. So yes, I could have used the mapping formula, but all I'm doing is, if I know I'm just moving things up or down, then that's pretty easy. Vertical translation changes what? Circle the properties that change. Has the amplitude changed? That's the distance between the axis of the curve and the maximum or minimum point. And the answer is no. The axis of the curve for this one is the x-axis. For the parent function, that's the x-axis. The axis of the curve shifts when we shift things. So for the green one, the axis of the curve went up to 2, and for the red one, the axis of the curve went down to -3. So you can see that the amplitude is exactly the same. The period hasn't changed either. That's the length of one cycle. It's 2 pi radians for all of them. Nothing's changed. Domain is the same. The domain is all real numbers. It goes on forever in both directions for all three of these. The range has changed. That is something that's different. So we can circle that, or let's highlight it. So the range has changed. And as I said, the horizontal axis, or the axis of the curve, has also changed. I'm going to add that on there. That has also changed. Okay, let's take a look at a different transformation. Now we've got ones where we're looking at the a value. And so we're starting with cos. And again, let's make our scale go 1, 2, 3, 4, -1, -2, etc. And cos starts at +1. Again, I know 5 points off the top of my head for cos that'll make it super easy for me to graph whenever I need to. And here it is. I'm not saying it's a beautiful graph. I'm no artist, but at least I got the basic shape. So that's the parent function again, in blue. And something on my screen. And the next one has got an a value of 2, a vertical stretch of 2. So if I look at all the y values, again, I could go for the mapping formula, but let's just look at the y values for those 5 points that I've got here, okay? If we take those 5 y values and multiply just the y values by 2, while keeping the x values the same, what we get is 0.02, pi over 2, 0, pi -2, 3 pi over 2, 0, and 2 pi 2. So it stretched it away from the x-axis. Hasn't shifted it, it's just stretched it. Any value that was 0 is unaffected, like at pi over 2 and 3 pi over 2. All the other ones became twice as far away. And the next one, we've got an a value of -3. So we're going to take all those original y values from the blue graph, and we're going to flip it in the x-axis, and we're also going to multiply them by 3. So 1 times -3 becomes -3. 0 stays at 0. -1 becomes +3. 0, -3. So it's reflected and stretched. The vertical stretch changes what? Well, does it change the amplitude? Yeah, the amplitude's changed. The axis of the curve is the x-axis for all of these. So the amplitude is definitely bigger depending on what the a value is. The period hasn't changed. They still have a cycle of 2 pi radians. The domain does not appear to have changed. It's still all real numbers. The range has changed, though. The range for the parent function, the blue one, was from -1 to +1. For the green one, y equals 2 cos x, the range now went from -2 to +2. And for the third one, -3 cos x, the range goes from -3 to +3. So that definitely changed. Horizontal translation, okay. Well, that was, by my color coding, a blue. Sometimes that's called a phase shift. And again, let's go back to sign for a parent function. Draw my 5 points. Connect the dots. Oops, that's cosine though, isn't it? and back to sine. So I start at 0, 0. Okay, there's my parent function. This one has a d value of positive pi over 4. Now, pi over 4, that's a little bit trickier with a scale because unfortunately the way this scale is set up, it goes pi over 2. If I take 1/3 of pi over 2, that's going to become pi over 6. And if I take another pi over 6 and I get 2 pi over 6, which reduces to pi over 3. So pi over 4 doesn't actually fit on our scale very nicely. Luckily, pi over 4 is exactly halfway in between these two. You could figure this out by getting a common denominator. If I made the common denominator for these three fractions 12, this one would be 2 pi over 12. This one would be 4 pi over 12. And this one would be, making a mess, 4 pi over 12. And this one would be 3 pi over 12. So 3 pi over 12 would fall exactly halfway in between these ones. But that's messing things up. So let's get rid of all that and just leave the dot, in fact. All we need is the dot. So we know the dot is there. So what's happened is we've moved, as far as our scale goes, we've moved everything 1.5 blocks to the right. So that means that this point here is going to move 1.5 blocks to the right. And this point here is going to move 1.5 blocks to the right, and so on. And this one, it's off the grid, but I can sort of aim for it. I'll put one over here. Connect the new dots. And actually, that one shouldn't have been up high. It should have been down on the x-axis. So I'm aiming for this. And I could backfill towards the x-axis as well. And this one has got a d value of negative pi over 6. So we saw that 1 block was equal to pi over 6. We're going to move 1 block to the left now. So we'd have one about here. The blue one, the 0, 0 would move back to about here. I'm looking at my parent function, these blue ones. And so this point here would move back 1 block. And this one, and this one, and this one. And again, there we go. So that's the phase shift, and it doesn't change the amplitude. It doesn't change the period. Yes, everything's been shifted, but basically if you look at the beginning and the end of each of these different graphs, they've completed one full cycle and are ready to start over again. The domain doesn't change, still all real numbers. The range doesn't change. So none of the above. It doesn't change any of these things. The last one is the k value, the horizontal stretch. We find that inside a function, and that will make things either stretched or compressed horizontally. It could also reflect it in the y-axis. Let's start with our basic cos graph again. Okay, there's my 5 points. There's me connecting the dots. There's cosine, parent function. This one, because of where that 2 is, that makes it a k value. That's going to compress things horizontally. So again, what does that mean if I compress things horizontally? If I look at these 5 points, a horizontal compression, I'm going to cut it in half. I'm going to make it 1/2 as far from the y-axis. So if I take my x values and cut them in half, it'll make them closer. So this first one here has already got an x value of 0. If I cut that in half, it's still 0. So I still have a point in the same spot. This one I got to go halfway back to the x-axis. So visually, that's going to be right here. This one, halfway back to the x-axis, takes me to here. And I just keep doing that. Oops, too high. Wrong place, I'll get it. There it is. Okay, connect the dots. Same shape. And I should keep going though. It's bad form to stop there, so if I've got more room left in the graph, just keep following the pattern. You can see that there's a new dot every block and a half horizontally, and they keep following that up and down pattern. So just keep going until you run out of room. Okay, the last one has got a k value of 1/2. Now remember, that just means it's actually going to be stretched by a factor of 2. If we were to use them, we could use that mapping formula again, right? So I could do the table. I've been avoiding that up to now because it's not necessary, but I want you to know that it is still possible. So we had parent, stretched, final. Usually we have multiple transformations going on at once. That's why we use the table. For each one of these examples, we've had only one going on at a time. And in fact, it still feels like a bit of a cheat to do this one. So why would I need to use the table for just a k value of 1/2? I'm going to make up one more example afterwards just to show you how it works. So k value of 1/2. Color these. All right. So take all my highlighted yellow, blue dots and double the x value. So this first one, if I double 0, it's still 0. For this one, if I double pi over 2, it becomes pi, keeping the y value the same. For this one, if I double pi, then I get 2 pi. Again, keeping the y value the same. And I've already run out of room. So really all I'm going to get is half a cycle in here before I'm out of space. But that's okay. Okay, so just to show you that we can do this with the table, let's make one up. Let's say y equals, keep it fairly simple, 2 sine, no, let's go cos since we're going to do it on the bottom. Stick with the cos. 2 cos x plus 1, no, x plus pi over 6 minus 2. Okay, k is, there is no k value shown, so we can skip that, it's 1. D is going to be negative pi over 6, and c is going to be negative 2. A, k, not k, D, and this is C. Okay, what are my parent points? Well, those are those points that I highlighted in yellow that I started with. So 0, 0, 1 in this case for cosine. Pi over 2, 0. Pi, negative 1. 3 pi over 2, 0. And 2 pi, negative 1, positive 1. Okay, k value. As we said, there's no k value. So if I'm using the mapping formula, which was xy maps onto x over k plus d ay plus c, then there's nothing to divide by. All my x's are going to stay the same for the first step. And I'm going to multiply all my y values by a, which was 2. So I get 2, 0, negative 2, 0, 2. Then I'm going to add my d value to all my x's. This is probably the most difficult because we have to add fractions. Don't let the pi throw you off. So I'm going to add negative pi over 6. I'm going to subtract pi over 6. So I get negative pi over 6. Now I have to do a little bit of conversion. Pi over 2 is the same as 3 pi over 6. So when I subtract, I get 2 pi over 6, which reduces to pi over 3. A little bit awkward, I agree. Pi minus pi over 6 is 5 pi over 6. 3 pi over 2 is the same as 9 pi over 6. So when I subtract pi over 6, I get 8 pi over 6. And then 2 pi, I get 11 pi over 6. So you can pause this if you want to stop and think about those fractions. They should all work out, but I went fast for sure. Last thing is I'm going to add my C value to all my middle C values of this column here. So again, I'm just following the exact same pattern. I'm just going to subtract 2 from everything. And so I get 0, negative 2, negative 4, negative 2, 0. And as usual, these are the points that I have to plot. So negative pi over 6, again, is going to be one block off to the left and 0. So my first point is off to the left a little bit here. Then I got pi over 3 and negative 2. Remember, pi over 3 was this mark here on the scale, but I have to do it at negative 2. So it looks like if I can even count my blocks, 1, 2, 3. If I go over 3 blocks, I get to my next point. It's going to, whatever the pattern starts with, it's going to continue with. So I know for a fact that if I count over 3 blocks from this point, I should be able to get to my next one. So 1, 2, 3, and then go down to the value of negative 4, and that'll get me to the next point I need. And then 3 more blocks, and then back up. 3 more blocks and back up. And connect the dots. And so this is a more complicated transformation that throw in that last bit that you can see using the table works on. A couple of things to tidy up just for the end here. Compare the graphs of y equals sine x and y equals cos x. Okay, well, we know that they look exactly the same. In fact, where do we have them here? This blue one, there's sine x. This blue one is cos x. Maybe with the other stuff in here, it's hard to really focus on them. They have the exact same shape. They have the same amplitude. They have the same everything, except one of them looks like it's been shifted compared to the other one. So in its most basic form, if sine x looks like this, then cos x looks like this. So same height, same period, you name it, same axis, just that the cos one looks like it's been shifted to the left from the sine one. Or the sine one, you could imagine if you took the cos one and shifted it to the right. So we could think of the cos graph as being a transformation of the sine graph. So we could think of cos x, stick with the green color since that's what I had for cos x. Cos x as being equal to sine x plus pi over 2, because that's how much they are apart. Pi over 2 would be the phase shift. So if I had taken the sine graph and shifted it to pi over 2 to the left, then I'd get the cos graph. Or vice versa, I could say that sine x is equal to cos of x minus pi over 2. That would be taking the cos graph and shifting it pi over 2 to the right. Compare the graphs of y equals cos x and y equals tan x. How does the location of the asymptotes on the tangent graph relate to the value of the cosine graph? We talked about this in the last lesson, so I'll just quickly remind you that, remember, there were tangents. Tan x is equal to sine x over cos x. So wherever the cosine graph equals 0, the x-intercepts, you get tan x is going to have an asymptote. And that's it for this lesson. You can read over the key concepts, and of course there's homework to work on.